Buenas tardes. Hi. Good afternoon, everybody. I'm Rafael Arana, Senior Solution Architect from Cloudera during the last 4 years. And I was co-presenting with one of my colleagues, Sulin Kang. He's from China, but I'm sorry to say that he could not make it. But I will try to cover his part, okay? So today I'm going to talk about parallel and distributed model training and Cloudera Data Science Workbench. So if you are here, it's probably because you are doing something related to machine learning or something related to data science. So who is already implementing models and struggling with long-running training times in the audience? Yes, so you're looking to improve those times, I expect. Who has played a bit with Cloudera Data Science Workbench? Nobody? One? Good. Okay, so I will try to do a quick introduction about what is it. But for today, the menu is, first part, do an introduction about why I want to talk about parallel or distributed. What is the business needs in our customers today, in your customers, in your enterprise? And we will go a bit deeper into different options to do distributed training. What are the different paradigms? What are some of the frameworks outside that implement those paradigms? And in the last part, I will try to cover how to integrate some of those solutions inside Cloudera Data Science Workbench, okay? So first, deep learning, machine learning is, as you already know, is everywhere. We have customers, some of the car retailers that are building, of course, building automation on all the vehicles is the next big expectations, and nobody wants to be the next BlackBerry in the car industry. It's one they are investing a lot in all the car manufacturers in deep learning. They are implementing devices that use a lot of image recognition, object detection, and all that stuff, as you probably know. Smart cities is also a big need. We have governments, we have cities that are implementing surveillance solutions using deep learning, or just simply IoT for optimizing energy consumption. So a lot of different use cases in smart cities. Devices, so all of you have a device with tens of models using deep learning inside to do the inference from email, from your personal assistant in your mobile. You already know. One of the big markets is healthcare and image detection. Radiologists improve the cancer detection. There are a lot of research done in that option. And of course, it's going to take some time to put it in practice because there are a lot of regulations, and we are talking about our own lives and cancer, things like that. So it's quite sensible, but from the technical perspective, it's a very challenging and interesting thing. So, sorry. Yeah. Probably you recognize this. Have you seen this movie? Yeah, Total Recall. It's a nice scene when Arnold, that is playing the role of Quaid, jumps into a futuristic cab, and there is a kind of robot dressed in old-fashioned cabby mode, and he starts to ask, or try to interact with the robot, and the robot is trained to ask you where you want to go. But he received a question, and the model is not properly trained to handle that event. It's one of the challenges that will bring a lot of workloads in our real use cases. So the question is, the important one is, what I'm doing here, and it says, I'm sorry, would you rephrase the question? And then, how do you get into this taxi? The door opened. So it's what it's trained to. We need to have a huge amount of data and more complex models to handle those kind of situations. Okay. Takes time. So I don't know if you have seen this, the increase in compute. And mainly this is caused because we are adding more use cases, more complex use cases to our neural networks. And you can see from AlexNet in the 2013 to AlphaGo, one of the latest famous and hot topics in the media. So this is interesting because it's logarithmic scale. So it's growing, it's doubling every 3 months the computing power. So the demand is amazing. We need to be aware of this when we design our system architecture, when we take in place which platform do I want to run to scale to these needs, because this is going to be growing and growing year after year. So I'm talking about training. What do we want to train? We want to train a model. Where is the model? Is that a small box at the right, bright blue? But there is a life cycle around our model. First, as usual, it starts with data. We need raw data, our events, our images captured in a car, our is it a speech recognition, is the words you are trying to translate. We need to do, after collecting all that data and store it somewhere, we need to do the feature engineer. We need to get the numbers in a proper way to put it in a program and get some prediction. So that's the feature engineering. I don't want to go in the whole details, but just I want to show you that, okay, when we have our numbers, our features, we're going to use a machine learning algorithm to find out a function that will do this prediction. So if I have X, I want to find out Y. If I have an image with a dog and a cat, I want to find out if this is a dog or this is a cat. Okay, that's the function. And my machine learning algorithm is going to go through the different options, functions, and we will define a loss function. So how far am I from my proper prediction to run the perfect model? So at the end we need to have a goal. And once we have that goal, we want to validate it on some data or run a test on data that has not been seen by this model. Okay, once we have a model with a proper accuracy, we need to put it in production. In production, we want to run a prediction, and for that prediction, we're going to have fresh data that the model never seen. And again, we need to do some kind of feature engineering, transform my image in numbers that will be the input to my model, and run a prediction to get a target. But the input is the data. How much data do I need? We always see in the media, you need the more data you have, better prediction you will get. But can we measure that? Is that can be proved? So this is a research from Bay2, and they ran different machine learning algorithms, and they have found out empirical proof that there is a power of law. So most of you, when you start with machine learning, start in the small data region, you don't have enough data to train your model. So it's just a random guess. As we cross into the power law region, is data that is providing value to our model, is discovering new things. We are going to get a better generalization of my model. Okay, so we are in the power law region, and this guy has shown that the more data we add, we grow by a power law that the slope will depend on my model, how complex is my architecture. Is this a convolutional network? Is an LSTM, but the growth is logarithmic. For example, for LSTMs, they proved that growing the architecture, so you have model name parameters in millions in log scale at the left, and the size in millions of words in the X. You can see that the more words we provide to an LSTM or an RRHN, we get better accuracy. Okay, so first, we need a decent amount of data to be in our power law region. And the first challenge is, okay, most of our use cases is supervised learning. We need label data. Where do we get label data? So normally, we don't have enough label data. We can try to reuse data sets. There are a lot of public data sets to run research or run experiments. In the real use case for a lot of enterprises, we don't have that data. We need to have someone doing the labeling. Or we have a small amount of data, and we can use techniques like data augmentation. So we can have our data set and run, using machine learning or any other kind of algorithm, increase the amount of images we have or the amount of training and label data. But other challenge is in real use cases, we are talking about data from our customers, our people, citizens, and we have to meet the regulations in Europe, GDPR. All international companies working in Europe are also to be compliant with GDPR. So it's another challenge. How do we handle proper label data and within security and inside a regulatory environment? So what we can do if we don't have enough data? We can try transfer learning, and my advice is, as a first approach to a scale, if you don't have enough data, try to find out if there is someone outside that have run a similar problem and they have published the model. The model at the end is just an amount of weights and parameters, an amount of numbers that can be reused for your problems. So in that case, I took this famous disk where you can take a ResNet, download the model, and run a Keras model, and it predicts pretty good the persons with different probabilities. It predicts the cards, but if you take a closer look to the second guy, I think is Ringo, there's something on the leg. Yeah, it detects a skateboard. So yes, transfer learning is good, but normally for real problems, if we are a car manufacturer and we are building an autonomous vehicle, we need to do something else. We will need to try to solve those problems. We will need more data, and we can, if you have a small amount of data, we can reuse all the layers and just replace the latest ones. If we have a decent medium amount of data, we can replace only the latest layers, or if we have huge amount of data, we can use this model to as initialization of my model. But it's one of the things that we can solve. The architecture, what kind of architecture? Deep neural networks, the more deeper, the better. Is it always the same? So probably you have seen this kind of diagram or something similar. So we have our training set that we know it must be big. We have an architecture. An architecture in neural networks is an amount of layers. How many layers? We have different kind of layers. So at the end, these are building blocks that we can combine. And you can see on the right some popular examples, a VGG or a ResNet with different amount of layers. This can be quite complex. And at the end, we have one problem is we need too much data, how to handle that. And now we are introducing another potential problem. The bigger my network is, more memory I will need. There will be more layers. For each layer, you can see different circles. Those are numerical numbers that we need to use in our computations. So it's one of the challenges to scale. So normally, the deeper the network, the better, but it's not always true. We need to be aware that sometimes with some small changes, we can get more or less the same accuracy. So in that case, you can compare VGGs with GoogleNet or NIN. It's different kind of architectures. The trick is that they reduced the amount of parameters in the fully connected layers. One of those kinds of layers I saw you before that are at the end can be many fully connected layers. The less you add, less memory impact you will have, less parameters. Or for example, for convolutional networks, a convolution is just a matrix operation. So you need to run a filter, and that filter is just a matrix 1 by 1, 3 by 3, or 5 by 5. But you need to run that operation millions of times. So in GoogleNet, they reduce the filter to 1 by 1 compared to VGGs that are 3 by 3 or 5 by 5. That reduce the computation overhead. a lot. So not always a more complex, bigger network means better accuracy, something to also consider. So, okay. We finally have the amount of data. We have an architecture. We can do transfer learning. And we run in, normally we start with a small laptop. We move to probably a container or a small machine. And we get a decent amount of accuracy. And what we realize is when we put this into production, the accuracy is not so good. So normally, our model has been trained with a certain amount of data that can be from 6 months ago, or probably depends on the location. So a model that has been trained with data from Barcelona probably doesn't get the same results if you train the same in Budapest, because your users will have different data, depends on location, depends on time, a lot of different factors. The data is always in constant evolution. So at the end, we have a development life cycle, and we see again train there. So the first part of the project is, okay, we need to plan, design, do the data engineering. The first iteration, this can take 70% of your project. Finding the right features, getting the data, you run experiments. But once you go into production is when really starts your project, because it's a constant life cycle. You're going to find out that on production, the data is not the same. It's constantly changing. You need to monitor, experiment, and train again. And if that training is taking hours, days, or weeks, that's going to stop your innovation. You have an issue in production, and you need to run an experiment to solve that, and takes hours, your IT guys is going to put a lot of pressure on you. So you have a problem. Okay, so we want to try to find out solutions for that. So TensorFlow is probably one of the most popular frameworks out there, and most innovations in the market are going that direction. Is Python or C++, but most of you probably has tried it with Python. And it was conceived at the beginning with distribution in place, okay? So that's good. That is from Google. And what happened? These are really good technical guys, but from the usability perspective, I would say that they need to improve it, okay? And it's probably, it happens in all the technologies. First it works, and then we need to make it more usable to the audience. So they conceived some APIs, the distributed TensorFlow package. Probably some of you have trained, give it a try. You have to configure a cluster spec where you say, okay, have 2 parameter servers, 3 workers, these are the IPs, these are the ports. That is in your code. And you have to assign different roles. And they conceived the idea to have a parameter server. That is a process where you have the state of your model. So your model is on that guy. That guy is in charge of updating the parameters and update the gradients. And you have the workers. The workers are the guys that are going to run the heavy computation, those metrics, those filters, or the activation functions like ReLU or other different mathematical functions are normally run in the workers. But at the end, it means that you need to send information through the network between the workers and the parameter servers. And we were talking about huge amount of data to have decent accuracy, or having a deep network so my model can have millions of parameters. And that could mean a huge amount of data through the network. And normally, in those use cases, if your model is really big, or your amount of data is really big, there's going to be a bottleneck on the network. Okay, so it's one of the limitations of this. You can add more parameter servers, but at the end, there is some considerable drawbacks. So the guys at Google realized that, okay, the API is not the best, so let's try to wrap it. And they have created a new distribution strategy API that simplifies the things a lot. So it's available in one of the latest version of TensorFlow, 1.12, 1.13. But they're gonna, but it's still in evaluation. Let's say it's a bit buggy, but in TensorFlow 2, that is already an alpha, will be part of the core of TensorFlow. Now it's part of the contribution. So the good thing is we don't need to take care about the IPs of my parameter server or my workers, or how many CPUs or GPUs I have in my machine. So this API will take that in charge. It will try to find out how many GPUs and try to assign the tensors in the optimal way. Of course, one of the good things of TensorFlow is flexibility. So you are going to be able to do that if you need to. But in most of our use cases, we don't want to spend so much time unless you are doing a deep technical research paper, okay? So they have developed this distribution strategy for Keras or also for estimator. And as you can see, the model is almost the same. It's just you have to instantiate a mirror strategy and use that in your configuration. Okay, so this is the first option I wanted to show you. But how to distribute the model? So let's step a bit back. When we want to distribute a model training, what do we need to distribute? What is a model trained from an algorithmic perspective? So we have an amount of data, okay? We have a function that is our model, and we provide to our model, we provide the x, the values that we have, our labeled data, and we get a prediction. That is the prediction tensor. So we have a tensor. We are trying to find out if this image is a cat or is a dog, okay? In the first iteration, probably we are not close to the good results. So probably I ran my model, I'm here, but I know it's a cat and I should be there. Okay, what can I do? Let's find out how far am I from the proper value. That is the loss function. Okay, I know this is a cat, and I get that I'm a dog with a 20% of probability. Okay, I need to move in that direction. How far am I? That's the loss. Okay, which direction should I move? That's the gradient. In mathematics, is the gradient. Okay, and I will take a bigger step or a smaller step. That's the learning factor. So at the end, we are doing that for all our images. And it's multidimensional, normally, features. It's not one dimension. So it's not a vector. It's not a matrix. Those are tensors, where we need to run this mathematical. And at the end, when we have the gradient, we want to update our function and say, OK, this was a cat. I was here. Now I want to be there. I need to update my function to be closer to my target. OK? So we need to update the model with the gradients. And we want to distribute all that. What can I distribute? I can distribute the data, because it's a huge amount of data. I can distribute the model, because if it's a really complex, deep neural network, probably doesn't fit inside the memory of one GPU. There are GPUs with 2 gigas, 4 gigas, some with 12 gigas, depending on what you pay. Normally, in most of the cases, your model is going to fit in that memory. But how do efficiently can distribute the parameters or aggregate the parameters? So those are the challenges that we need to address. So the first option, as I mentioned before, is TensorFlow started with a model parallelism approach. The idea is, OK, Google, they have really big models. Probably none of us are going to have to implement those in our customers or in our enterprises. They need to scale the model. They split the model across different workers, and they have a parameter server that tracks the information. The problem is that there is a lot of communication through the network, as I mentioned before. But it's one of the options. So my recommendation is, normally you're not going to need data parallelism. You can run an approach using a parameter server if you don't have too much information to send through the network. But there are better options, and that's where I want to suggest. So, okay, model parallelism only if you have a huge, huge model that doesn't fit in the memory of your normally GPU. Okay, so it will depend on your GPUs. Because as this graph shows and comes from Uber, in Uber they faced this problem. They started to use the parameter server approach, and they realized that the more GPUs we add, they expect some scalability. So you see two different graphs. Inception, ResNets are different architectures of neural networks, and you can see the amount of images per second that you can process with a parameter server approach using TensorFlow. And you expect, okay, let's duplicate the amount of GPUs. Should I scale to a double amount of images? But it was not the case. There is a significant overhead through the network, and that's what took them to go into another direction, and that's how they created Horovod that used a different algorithm that is named ring-all-reduce. Sorry. So, what's data parallelism? Okay, so as I mentioned, in most of your cases, your model is going to fit in one machine. So, probably your data set will not fit, or it will be really high. What we can do? We can split the data across multiple nodes. Okay? Again, we need to do the same. We have a model, we check how to get the gradients, we average the gradients, and update the model. But part of the process, the first part, the model and finding out the gradients is run on every machine. At the end, when you want, you collect the gradients for each machine and do the average, and with that you update locally the model. That's the idea of data parallelism. So what is ring-all-reduce? This is what I was mentioning, but it was created by these guys using HPC per computing approaches using MPI. That is a framework that allows you to communicate through the network between different processes. But this algorithm has been one of them with more success and is already available in Horovod, Beidou, PyTorch, MXNet, and will be in TensorFlow 2 also probably. So it's one of the best approaches you can go if you don't have a huge amount of GPUs. We mentioned that the network is normally one of the limits. So we have to send all the gradients. If the amount of gradients is really big, that can mean an important limitation. Is RDMA what we need? What is the benefit of using RDMA? So it's, it's normally implemented with INFINIBAND. It's a high, expensive protocol that will give you much more bandwidth. So the question is that using an all-ring reduce, you put much less pressure on the network. And only for some models like the one on the right, a VGG16, you get a significant benefit of using RDMA or INFINIBAND. So my advice is, if you go for an algorithm like ring-all-reduce, your limitation is not going to be probably on the network. Invest in more GPUs than in a highly expensive network infrastructure. And it's not only expensive, because the other drawback is you need to have drivers to use RDMA, and those drivers needs to be available in your frameworks, in your platforms, in all your technologies. So normally it's a significant investment that only you have a case like the one you see with VGGs 16 makes sense to do the investment. In the case of the VGGs is, as I mentioned, they have a lot of fully connected layers with huge amount of parameters that put a lot of pressure on the network. That is where the bottleneck was. So it will depend on your use case, it will depend on your network, but normally it's better to invest in more GPUs than in an RDMA network. Another thing to consider is when I synchronize the parameters, how do I do it? Do I do it in a synchronized way or in a synchronous way? So normally, if you go for a synchronized approach, all your workers need to sync after the training. Okay, that means if the drawback is if one of your workers is lagging behind, is going down, you have an infrastructure problem, your framework needs to be aware of that. That is the problem. But normally the accuracy and the model converge much more faster than if you go asynchronous. In asynchronous, it will be faster, but it's much more difficult to converge. Will be an stochastic approach. So it will depend on your model. My advice is give it a try. And it will depend. There are some algorithms or frameworks that it's quite easy. You just need to provide a parameter to say, okay, I want it synchronous, I want it asynchronous. But there are others where it's not so easy. Other thing to consider is we are sending these gradients through the network. And we have a huge amount of layers. And the size of the information we send will depend on the batch side. How much data are we running in every cycle? And normally, traditionally, in most of the research papers, they use a small amount of batch size. These guys proved that with a ring ALLREDUCE, it's much better to use a bigger batch size because you're moving more information through the network. You do a better usage of your network. And in that case, they proved that they have the hotspot with 8,000 mini batch size, something that is not normally when we run some basic experiment in our network. So depending what frameworks are there, so Microsoft normally goes for a synchronized and Uber Horovod. Google by default use the parameter server approach with an asynchronous, but you can also change it through the code. Okay? Sorry. What's the difference when we update our data using a synchronized stochastic gradient descent? It's quite different. Not really, it's almost the same. So only we need to be aware that when we update the global parameters, there is a W, T plus 1 is for every iteration we need to update with the previous and using our learning rate is how big is the step I want to take, okay? So in the case of a distributed environment, normally you need to adapt that number, the learning rate, to the amount of workers. That is the K. So, okay, we have different options how we do this in model training in Data Science Workbench. So what is Data Science Workbench? Probably you already know is at the end is a service where you have a web UI that can spin containers. Those containers, there's a master, can be engines, are Docker containers running and orchestrated by Kubernetes. So what do we need? We want to run Horovod or TensorFlow or GPUs. But at the end, we just need to create an image with the proper requirements that normally will be stored on a Docker repo because we want to have predictability. We are going to have a cycle and we are going to change that image in the future and we're going to update the drivers of CUDA, the GPU or whatever. We have our code. The code that we are going to run, normally Python, but can be R or can be Scala, or normally that will be a story in a source repo in Git. And we have data. That data can be in a cloud storage or can be in a Hadoop cluster that can be from the CDH or can be Hortonworks HTTP, and all can be managed through Cloudera Manager or Embari. Okay? So at the end, what we get is a container where we can make use of the resources in the machine. So that container can have a different amount of CPUs, can have different amount of GPUs. And within our container, we can run different frameworks. So you can run TensorFlow, PyTorch, Keras, whatever you prefer, okay? I want to scale. So the first thing is, okay, I want to add more GPUs. How do I need to update and add more GPUs? So first, let's create an image in Docker Hub. And in that image, we want to install all the dependencies from NVIDIA drivers, for example. You want CUDA, you want NCCL, Nickel, or the deep stuff that will close the gap between our TensorFlow and our GPUs, okay? So normally you put that in your image, you publish that in your repo, and you just need to tell your admin guy, the admin guy, please register this image in Data Science Workbench. So you can just point there, and then you have your image available to your project. So you go to your project that probably was using CPUs, and now I want to give it a try with GPUs. So I need a new image that includes all the information to run on top of NVIDIA. So reference that GPU, and yeah, you can use it. How can I run this with a distributed architecture? So the good thing is, normally, most of the cases, you just need to run one container. And in that container, you can spin up multiple GPUs. If you want to run more containers, Cloudera Data Science have an API that allows you to instantiate more containers. I will show you an example. So we can create an image where you put your favorite framework like TensorFlow or PyTorch. And if I want to use Horovod, I will install Horovod. And I can spin up my containers, and they will talk to each other to do the distributed training. So I was mentioning there is an API, how that works. So on the master.py, you can see that you have a data science workbench.launch workers. And you can say, OK, I want 2 workers more. I want 4 workers more. And I can specify, OK, how big are these containers? I want 1 CPU, 2 CPUs. In particular, you can, it doesn't need to be an integer. It can be 0.2 of CPU. And how much memory? Half gig of RAM, 32 gigabytes of RAM. And you can specify a Python script that will be run in that. Now, this is one of the approach. So here shows a quite basic example of how to do that. So for creating Docker images, the only restriction is you need to start your image with the image that we provide. Okay, so it's just an Ubuntu image. At the moment, we only support Ubuntu, not Red Hat. And on top of that image that is referenced in our public repo, you can install your needs. You can normally you will install all the dependencies to run GPUs like NVIDIA stuff. Or if you want to run Horovod, you need to install OPEN-MPI, things like that. It would depend on your architecture or your use cases. If you want to put something else like your framework, if you have a big company where you have a big teams, normally you can define some best practices. I want to use TensorFlow 1.12 in all the teams. My experience is that's not the case. Normally, data science teams are decentralized. There is one per business unit, and one guys prefer PyTorch, others prefer TensorFlow, or depending on your use case, one day you use one, the other day you use the other. So normally, you don't need to add those frameworks as part of the image. What you can do is once you instantiate your image, you can install them, okay? Or we already have some images that is not part of the product, but developed by some of my colleagues. You can find the reference there and download it and give it a try. So one important consideration is, I don't know if you already have worked with OPEN-MPI. Any experience out there? FDN is a framework that allows you to spin up processes and talk to each other. And normally it's a command line tool that at the end triggers a script. So one option is to do that. The other option is, okay, go directly for Python, because normally in Cloudera Data Science what we trigger is Python scripts. So you can encapsulate that as part of the triggering. So what do we have around the corner? There are a lot of initiatives in the market to run distributed training. Probably some of the more interesting are Spark on Kubernetes, GPU support for Yarn, things like that. There are a lot of open source frameworks. Horovod is already can be run on top of Spark. And the good thing is also that TensorFlow is moving into that direction of using other algorithms like ring ALLREDUCE. So TensorFlow 2.0 will implement that. It's at the moment I think it's in alpha, but probably will be released during the summer. And I think it's really a big ecosystem that is growing really fast, and we're going to have a lot of interesting projects and initiatives that you can put inside your containers and orchestrate with a Kubernetes cluster, with or without Data Science Workbench. Okay? So thank you. Yep.
Thank you. It was an excellent presentation. So I have two questions. The first one is about, you talked about the gradient averaging between the containers. This communication between containers, how it's done? So is it managed by the developer itself? So he should manage in the Python code how it's done?
The good thing is that normally covered by the frameworks. So most of the frameworks like TensorFlow or Horovod take care of that. Okay. And well, and in TensorFlow, for example, you need to define which the current version. You need to specify which GPUs you're going to have for each worker. With the new distribution strategy API, it's going to be much more easy if you want to go for the easy approach. Okay. But you still have the backdoor to, okay, if I want to do it and I have the knowledge, I can still do it.
Okay, thank you. So my second question is the data architecture around it. So how, for example, the data, how we feed the platform with data?
So yes, it will depend on where is your data. So normally, most of the people start with a local storage on the nodes that run the computation. But once your data starts to grow, you need to find different options. So if you are in the cloud, you can use cloud storage, scalable, S3, or Google options, or Azure, ADLS, things like that. If you are not on the cloud and it's an on-premise, and normally that data is stored on Hadoop, and you need to connect to Hadoop to retrieve the data.
Okay. Okay, thank you.
Any other question? Nope. Okay, guys, thank you very much for your time and attention.